Welcome to Oddly Real. I'm Nem Stefanovic. In this episode, we're going to travel through four-dimensional spacetime, which is 3 dimensions of space and 1 dimension of time, to understand its structure and how it behaves. Although it might seem natural to think about space and time separately, the reality is that space and time are truly intermixed in our world. You'll see that when we move through our universe, there are very strange implications for what we experience in both space and time, depending on our frame of reference. What we measure as observers in spacetime is only part of a more foundational and more real underlying structure that exists in spacetime geometry. For example, imagine you deviate away from a straight line path between two events that happen in spacetime, only to find out that the distance that you covered was actually less than if you'd stayed on a direct path. Also, certain motions through spacetime will actually aid you less than others. We'll explore various strange and counterintuitive features of our four-dimensional spacetime geometry within our universe. There was a time over 100 years ago when many scientists thought that the science of physics was almost completely solved. Isaac Newton's version of space and time prevailed and seemed to explain almost everything. Space had a flat Euclidean geometry that followed the same geometric rules that we all learned in grade school. Time was something completely distinct and ticked away at a fixed pace that set everything in motion. An object in space could be accelerated in motion using a force, and if you kept that force acting on the object, it would continue to pick up speed with no upper limit. Also, all of the universe was set against the backdrop of a mysterious universal medium that permeated space called the ether, which provided an absolute position and velocity for any object. Unfortunately, this was all proven to be completely wrong. At the beginning of the 20th century, Albert Einstein introduced a whole new theory of relativity that had major implications for the properties of space and time. In complete contrast to Newtonian physics, there is no absolute position or velocity of objects. It's all relative to what they're being compared to. There's no universal ether. There's also an upper limit to how fast anything can move, which is the speed of light. Finally, space and time are not separate, but are inherently coupled together, connected, in a single four-dimensional fabric with startling implications when we traverse through it. In order to understand spacetime, it is important to understand the concept of the principle of relativity. You should be able to conduct an experiment of any kind in a room which might be at rest or moving at a constant velocity. The usual laws of physics should not change. They should always be the same. In fact, if the windows of the room were covered with blinds and you couldn't see outside of the room, you shouldn't be able to tell if the room was moving or not, and you shouldn't know its velocity. This state of the room would be considered the inertial reference frame. Other rooms with other constant velocities would have different reference frames, but the principle of relativity would still hold, and the laws of physics would remain the same there as well. Additionally, since the laws of physics remain the same for all observers in all reference frames, that means that the speed of light too must be measured to be the same in any reference frame. The basic components of spacetime are made up of the familiar 3 dimensions of space and 1 dimension of time. We also refer to this spacetime as Lorentzian. You'll soon see that the properties of Lorentzian spacetime are very different from Euclidean 3-dimensional space. Interestingly, it turns out that the dimension of time has some similarities to the other dimensions of space. Time is different from space, since it only allows traversal in one direction, forward. However, it can be measured in the same units as space, which is meters. It turns out units of time, like seconds, are just an alternative measurement of the same quantity, meters, with a conversion factor between the two being the constant of the speed of light. So 3.336 nanoseconds of time times c, the constant speed of light, equals 1 meter of time. The constant speed of light turns out to be just a conversion factor to unite the dimension of time with the dimensions of space. Locations in spacetime are called events. An event is necessarily composed of both a component in space as well as time. For example, I throw a baseball. That's an event. The baseball collides with a bat. That's another event. Most importantly, events are part of the absolute reality of spacetime. They occur and all observers agree that they happened and are real. Interestingly, observers in different reference frames will disagree about their measurements of the times and distances between the occurrences of each event. Even though the events themselves are absolute within spacetime, the observers only have a partial view into spacetime. Another absolute feature of spacetime is the spacetime interval, which is a measure of distance between events in spacetime. Just like we're familiar with measures of distance between points in three-dimensional space, a spacetime interval is a measure of distance in four-dimensional spacetime. The spacetime interval is also real and absolute, and it is found to be the same between observers across all reference frames. It's fundamental to Lorentz spacetime geometry. The spacetime interval is more real than what any observer can measure about space and time separately. We can compute the spacetime interval from an observer's measurements of space and time separation between two events as the spacetime interval squared is equal to the time separation squared minus the space separation squared. Events and spacetime intervals are enough to completely define all locations within spacetime, regardless of the reference frames of the observers. Imagine we have three different reference frames: a normal rocket, a ground laboratory, and a high-speed rocket. Let's first consider an experiment happening within the normal rocket from the perspective of the observer within the rocket. A beam of light flashes from the floor up to a mirror on the ceiling, where it is then reflected back down to the floor at a receiver. The beam of light takes a straight path up a distance of 3 meters and a straight path back down for another 3 meters. The total distance traveled is 6 meters, where light travels at 1 meter per meter of time. Notice that the beam of light started and ended at the same spot on the floor. So it has a net separation in space of 0 meters. Then the spacetime interval squared is equal to 6 squared. The spacetime interval is computed as 6 meters. The observer in the ground laboratory sees the beam of light differently from their reference frame. Since the rocket is moving when the beam is emitted, the ground observer sees the light moving not straight up, but in a zigzag, moving at an angle up and over. It moves 4 meters horizontally in space and 3 meters up to the ceiling. It then moves back down 3 meters and another 4 meters further horizontally. The total length of the zigzag path is 10 meters. Since light travels at 1 meter per meter of time, it takes a total of 10 meters of time to traverse the total path length. The spacetime interval squared is equal to 10 squared minus 8 squared, which is equal to a total of 36. So the spacetime interval is then computed to be 6 meters, which matches the spacetime interval computed by the rocket observer. Finally, the third reference frame comes from within a high-speed rocket, traveling much faster than the original rocket. The observer in the high-speed rocket measures the flash of light traveling in the opposite direction. Again, it travels 3 meters up and back down. However, now the space separation is 20 meters. The total length of time needed for light to traverse this path is 20.88 meters of time. So the spacetime interval squared is equal to 20.88 squared minus 20 squared, and the spacetime interval once again is 6 meters. Yet again, the spacetime interval calculated by the high-speed rocket observer matches the other observer calculations of 6 meters. The invariance of the spacetime interval is an outcome of the principle of relativity. Notice that in all three reference frames, the vertical traversal distance never changes. This is true for any distances that are perpendicular to the direction of travel. If they did change, we'd be able to distinguish each reference frame from the other by changes to this distance. Second, the speed of light is preserved for each reference frame, regardless of their velocities. This directly results in longer travel times of the light in the lab frame and the high-speed rocket. Ultimately, these effects result in the invariance of the space-time interval. It turns out that we can directly travel along the space-time interval and experience it firsthand. The way to do this is to move from one event to another at a constant velocity. Remember, this isn't a motion from one place in space to another location in space. It is moving between events, so you have to pass through each event at exactly the right place and time. This is traveling in a path through four-dimensional space-time. If you do this, you can bring a stopwatch with you along your journey to record the passage of your time on the trip. Since you're directly traveling from one event to another in your frame of reference, you're not moving. The events are occurring in the same point in space, which is at your location. This means that the length of the space-time interval is now exactly equal to your stopwatch time, since the space-time interval squared is equal to time separation squared minus space separation squared, which is equal to the time separation squared minus 0. That means that the space-time interval is exactly equal to the time separation, which is your measured time. All other observers at rest or moving at different velocities will agree that your measured stopwatch time matches the space-time interval. We also call this stopwatch time the proper time. In fact, we can completely specify all of space-time by identifying events separated by their space-time intervals. Individual reference frames and observer measurements could be completely eliminated, and all of space-time could be fully mapped out using this approach. What happens if two events occur at the exact same time, but separated by a great distance in your reference frame? You can't travel between the events. There isn't enough time to reach one from the other. Interestingly, there's still an analogous way that we can directly experience this space-time interval separation as well. Instead of using a wristwatch to travel between the events, you have to use a meter stick or a distance measuring tool that you'll lay down in the space between those events. That would give you the space-time interval. Let's look at an example involving the measurement of proper time. The distance between Earth and our neighbor star, Proxima Centauri, is 4.3 light years. Let's say a starship leaves Earth traveling at 95% of the speed of light. From Earth's stationary perspective, it takes the ship 4.53 years to make the trip. However, the proper time as measured by the crew of the ship is computed as the space-time interval squared is equal to 4.53 squared minus 4.3 squared, which ends up being 1.42 years as the space-time interval. This is different from the 4.53 years that has elapsed on Earth. It turns out that the proper time between two events is less than the times measured by other observers in other reference frames. What does it mean to talk about time on its own in our universe? If someone on a rocket ship with a synchronized watch to ours were to travel away at high speeds and eventually return, the time they kept would be completely different from our own. It could be off by years. There is no single absolute measurement of time. The only time that matters is the time that is accumulated as a measurement between two events. Time is not a way to measure a location or part of space-time. The meaning of time is that it measures an individual history of travel through space-time. It doesn't make sense to talk about a time related to one event. One analogy for time is the reading of an odometer on a car. The car can travel from one city, like Toronto, to another, like New York, and it can continue on its journey to a third city after that, and so on. The car's odometer captures the history of its travels by adding up the kilometers between one place and another. It doesn't give the measurement of one particular place. It does not say that Toronto is 1,000 kilometers. In fact, that doesn't make any sense at all. You'd say 1,000 kilometers relative to where? Similarly, it doesn't make sense to say that an event in time is 1,000 years in space-time. It holds no meaning on its own. What does make sense in our analogy is mapping out different cities like Toronto and New York, and then providing a distance between them in kilometers. The measurements between cities make sense relative to each other, and the car's odometer is the accumulation of its travels between them. In much the same way, you can take a wristwatch to record the passage of time between two events as you travel between them in spacetime. We can create a spacetime diagram for a particular reference frame to help with visualization. Real spacetime is four-dimensional, which we can't represent on a sheet of paper. However, we can simplify the diagram to capture the essence of spacetime locations if we assume a single dimension of space. That way, we can draw space horizontally on one axis and time vertically on another. We can also arbitrarily pick a point as our origin, which will be our chosen reference point to compare against all other events in spacetime. The spacetime map can now be associated with coordinates in space and time for any event in the reference frame relative to the origin. We can now look at all events across all of space and time by looking at this one spacetime map. We can also travel through a series of events, one after the other, in a chain such that it creates a path through spacetime. We call this the world line. For example, let's launch a model rocket from our location and watch the events unfold from our position where we are standing still or at rest. We can call this event O, and we can pick that to be the origin for our spacetime map. We stand still after launching the rocket, but time continues to pass forward. We map our path through spacetime as moving straight up through the diagram along time. At the same time, our launched rocket is moving away from us, but time is also moving forward. Thus, the rocket moves both away in space, but also forward in time. Perhaps there is a brick wall a certain distance away from where we are standing, and the rocket collides with that wall. Let's define that as event C. We can also say that event A is just a point in spacetime to represent the position of the wall at the time we launched the rocket. We can also say that event B is the point in spacetime when we see the rocket hit the wall. The vertical line from event A to event C shows the rocket and the wall are the same location in space, and their separation is the time from the rocket launch to the impact. The horizontal line shows the rocket impact at C and relative to us at B at the same time. The separation of B and C shows the distance from us and the point of impact at the wall. A world line doesn't have to pass through two events in a straight path through spacetime. It can take a curved path. What does that mean for the distance traveled through spacetime? To understand that, let's first look at a simpler situation involving travel through space without time. If we travel through space and keep track of our distance as we move, we know that a straight line between 2 points would be the shortest path. If we deviated from the straight path along a curve, clearly the curved path would be longer. Strangely, this is not the case for spacetime. We can carry a wristwatch as we traverse the world line to keep track of the proper time, which is the actual length of the world line through spacetime. An observer in a laboratory watches your movement and measures points along your path. Recall that the spacetime interval is what we use to measure length in spacetime. Alternatively, from the perspective of the traveler, they encounter events at their location, so their measure of the spacetime interval is just the elapsed time between the events. The wristwatch time adds up the times we experience on the spacetime path. The traveler can take a curved path between points O and B, which will result in a total proper time measurement on their wristwatch. The laboratory observer can measure segments of their travel along the curved path and calculate the interval distances for each segment. The sum of those calculated values will add up to the wristwatch time in complete agreement. But now let's take an alternative path between O and B, a straight path between the events. In this case, the interval calculations of the path don't include a space separation component. It's 0. So the total spacetime interval is larger than the curved path. This is verified by the traveler who carries the wristwatch along that straight line path. Both agree the world line in a straight path in Lorentz geometry is longer than a curved path. A straight path also happens to be the natural path that a free particle would take to go from one event to another. So the natural free motion of objects is to travel along the path of maximal aging, which is called the principle of maximal aging. But why does the curved path look longer on a spacetime diagram if it's actually shorter in spacetime? It's because the diagram is an illusion. We can't properly represent spacetime lengths in Lorentz geometry on a flat piece of paper. One event in spacetime cannot cause another event if they are separated too far from each other in space. The speed of light is a limit to how one part of the universe can influence another. It's a limit on causality. Nothing can travel faster than light. Also, spacetime has another unusual property in that two events separated far away in space can have a spacetime interval of length 0, as seen from the spacetime interval formula when space separation equals time separation. This is what we call a light-like separation in spacetime. Most of our examples thus far have demonstrated time-like separation, where the time separation is larger than the space separation in the spacetime interval formula. But notice there's another situation if the distance in space is longer than the time separation. We call this a space-like separation. Then the terms on the right-hand side become negative. No need to panic. In this case, we rewrite the equation so that we switch the terms to make the result positive again. So what does this all mean for spacetime? We can visualize these scenarios together by partitioning spacetime into a light cone with an event A in the middle as our reference point representing the present in time. The actual cone itself is a boundary that is traced out by the limits that light can travel either from point A into the future or to point A from the past. The light cone has a future portion at the top, which shows what influence event A can have in the future in spacetime. It can influence what happens at event B, since event B is in the future light cone. Event A can also reach the event G with no time to spare, since that requires exactly the speed of light to make it on time. The light cone also has a past component in the lower half of the diagram. Here, event J can influence event A since it is inside the past light cone. Also, event H can reach A with no time to spare. The events within the cones have a time-like relationship with event A. The events on the edge of the cone have a light-like relationship with event A. What about event D? It is outside both the future and past light cones. Event D has a space-like relationship to event A. It can't be reached even if traveling at the speed of light from A. No effect at A can influence the event at D. We say that D lies in absolute elsewhere of A. Thank you for joining me on this tour of space-time. Remember, oddly real, really interesting.